Welcome everybody to the quarterly theory workshop. Thank you all for coming. This is a new format for us. This is the first of its kind. We're changing our theory seminar format to be a quarterly workshop that brings in 3 people to speak on a given theme in theoretical computer science. And so this is the first one. We're going to have one in the spring and in the fall subsequently, and it's going to be hopefully a nice change and also provide for more interesting discussion about that topic area. So this workshop is on algorithmic game theory and data science. And we have 3 really fantastic speakers here, Tim Roughgarden, Eva Tardosh, and Avram Blum. Just to give you a little overview of the excitement in this area for theoretical computer science. Algorithmic game theory is a field that emerged, I guess, over 15 years ago now, studying algorithms in a world where game theory happens, in the sense of it was initially motivated a lot by the internet, where we wanted internet algorithms to work well, and we realized that the entities providing the input to the algorithms on the internet might be strategically manipulating those inputs to get the algorithm to produce a favorable outcome for them. And how would you rethink designing and analyzing algorithms in that world where these inputs might be strategically manipulated? The other aspect of algorithmic game theory is taking a more algorithmic design and analysis approach to considering games that are more traditionally studied in game theory. And that has led to a very rich dialogue between game theory and economics about how we think about analyzing and understanding game theoretic phenomena in the world. I'm particularly excited about now the connection between algorithmic game theory and data science, which is the topic of this workshop. And data science is, of course, a very hot topic in computer science and even science broadly these days. For me, the motivation is the same as before. In the internet, you have these systems that have game theoretic issues happening in them, and you've got a lot of data. So how can this data help inform and help you understand the game theory, the economics, the algorithms of what you're doing? And game theoretic data is not like other data, because game theoretic data is data that you get that's in response to the system that you are running. And if you're thinking about changing the system to maybe making it better, well, this is not the data for the new system, it's the data for the old system. And so this requires you to do counterfactual inference and things like this that makes it the situation for data science much more complicated. There are a number of opportunities in this space that we'll be hearing a lot about today. One of them is how the algorithmic game theory changes when, instead of taking models as sort of distributions or whatever, you take models as samples from data. And so that's going to actually cause you to change the way that you think about the algorithms. Another opportunity that you have is instead of just understanding a game from the model, you can now understand the game from the data that you have. So if you have a bunch of data in a game, that can lead you to come up with a much more specific understanding, rather than a worst case understanding, but a setting of understanding of what happened in that game. And lastly, a topic that I personally think is very interesting is a more data-driven approach to mechanism design. Meaning, we have people who want to design games in some environment, and they have data from running games previously in their environment. How should they think about using that data in deciding what to do in the future? So it's a very rich area, and one that our speakers today have been pioneering. And so I'm really happy to have this program together. With that, I'd like to introduce our first speaker, who's Tim Roughgarden. Tim Roughgarden is from Stanford University and has been there since 2000, 2003, I believe, 4, after a postdoc at Berkeley. So he is one of the pioneers of looking at approximation in game theory and trying to understand the quality of equilibria from the lens of approximation. In particular, what's his work with Eva Tardoch, who's also here, really pioneered this area of price of anarchy, which tries to quantify the equilibria, quality of equilibria versus what you could have achieved if you coordinated everything. And for that work, he won the Gödel Prize and the Grace Murray Hopper Award. And more recently, and in fact, Tim was my co-teacher in the first game theory class I ever taught, which was a really fantastic experience. And that was also the same year we collaborated together on mechanism design in the Bayesian framework, which precipitated a big change in the algorithmic mechanism design community thinking about the Bayesian world at that time. And that was really a fantastic experience. And since then, he's been applying price of anarchy tools and mechanism design tools broadly in game theory. And now he's also very interested in this connection to data science. So let's welcome Tim.
Okay. Thank you, Jason, for the kind introduction. Thanks for coming, everybody. I'm happy to be back at Northwestern, have an opportunity to talk to all of you. Before I forget, so the first half of the talk is all joint with my PhD student, Rishi Gupta. Second half of the talk is all joint with Jamie Morgenstern, who was Avram's PhD student and now is a postdoc at Penn. So before I move to kind of connections to algorithmic game theory, let me start with an issue that may resonate with many of you. So it's probably happened at some point to a lot of you. A colleague walks into your office, sits down at your chair, and says, there's a problem I want to solve. I want to solve problem X. Say, the traveling salesman problem. You're an algorithms person. What algorithm should I use? And it's kind of a little bit of an unfair question, actually, right? So it's kind of like you go up to a doctor at a cocktail party. You find out they're a doctor. You're like, I have this fever that's like 100 degrees. What should I do, right? So why is it an unfair question? It's because you don't really have enough information to give an optimal answer to the problem, right? So the doctor's thinking, well, 100-degree fever could mean lots of different things which merit their own treatments. Similarly, for a computational problem, extra details of the domain might give you advice about which algorithm to use. So in the same way that the doctor might say, take 2 Advil. If it doesn't work, call me in the morning. You might be tempted to say, try local search. If it doesn't work, call me in the morning. So the point is, the right algorithm to use depends on the details of the domain. Okay? So let me pull out one concrete example from the recent empirical literature. There's dozens of other papers that would prove the same point. So Smith-Miles et al., they did something conceptually very straightforward, though the results are quite nice. So they looked at graph coloring, and they just took the sort of state-of-the-art, 7 state-of-the-art off-the-shelf graph coloring heuristics. That's here on the x-axis. And then, that's the color code, I should say. And then they looked at sort of all of the standard benchmarks of graph coloring instances, which were coming from different application domains. And then they ran all 7 algorithms on all of these benchmark instances, and they tried to get some understanding of which algorithm works well when. Okay, so they used PCA on some features of the instances to plot a graph like this. And what the takeaway point here is just that each algorithm has its own sort of region of dominance. Okay, so they're really incomparable. And so the implicit advice in a study like this is, okay, well, if you want to solve graph coloring, look at your data, look at benchmark instances or synthetic data or examples from the past, figure out which part of this figure your application domain lies in, and then use the corresponding algorithm. That's kind of the implicit takeaway in a study like this. Now, you don't have to stop at just committing to a single algorithm once and for all. You can also try to do something more fine-grained. Okay, and so one famous example of this is SatZilla by Leighton Brown and collaborators at UBC. So the idea here is rather than just commit to one algorithm, when you get a new instance, quickly compute some features of that instance, and based on the feature values, decide which algorithm to use. So they did this, for example, in SAT competitions. When given a SAT formula, they would just compute some simple statistics. Then they would, based on that, choose one of 7 state-of-the-art SAT solvers, run it as a black box, just based on the features they computed. And actually, they blew away the competition with this sort of meta-algorithm in a number of SAT competitions. So the point here is just that when you're trying to figure out what algorithm to use, it sort of depends on the details of the domain. Right? And That's kind of the practice of algorithms. And the question is, could we have a theory which mirrors that way of thinking quite closely? And so the proposal here is that actually, learning theory, as has been, sort of a bread and butter topic in theoretical computer science for 30 years, it's a really great way to think about this problem of application-specific algorithm selection. So you can talk about both offline learning problems, which I'll do next, or you can also talk about online sort of regret minimizing algorithm selection problems. I'm not going to talk about those, but there's some in the paper with Gupta. Okay, so let me tell you about the formalism. I'm going to first apply this formalism to algorithms. In the second part of the talk, I'll apply it to learning near optimal auctions. So the setup is as follows. There's some set of algorithms C. Okay, so I want to emphasize, we're not thinking about a scenario where you're going to design some algorithm from scratch for a problem. Okay, so often we think about that in algorithms research, but often that's not sort of the scenario in actuality. Usually there's a suite of algorithms which has been implemented, which you're happy to use, and you want to know which one to use. So maybe it's sort of 7 different SAT solvers. Maybe you're trying to figure out how to set parameters of some parameterized algorithm. Anyway, so outside the model, you are given a class of algorithms C for some problem. We've seen some finite examples. I'll show you an infinite set of algorithms next. And then there's some performance measure that you care about. Okay, so for a given algorithm A and a given instance Z of this problem, there's some, for example, the running time of the algorithm or the objective function value of this algorithm on that input. The theory is agnostic to the semantics of the performance measure. And now what we're going to do is we're going to think of an algorithm as a real valued function. The domain are all instances of this problem, all TSP instances, something like that. What's the range? It's the reals, and it's just the performance of this algorithm on this input. So we're thinking of an algorithm, if you like, as a vector indexed by instances. Okay? We're thinking about its full performance profile. All right, so let me give you, so I've given you a couple examples of sort of families of algorithms. Here's another one, an infinite class. So greedy algorithms is one of the main things we look at. And so you can talk about greedy algorithms very generally. I'm just going to illustrate it with a simple one. So max weight independent set. I'll give you a graph. You want a subset of the vertices, non-adjacent, and it should maximize the total weight. NP hard problem. But if you wanted to have a heuristic for it, one natural approach to independent set is to use greedy heuristics. So for example, you could go through the vertices in a single pass, always taking a vertex if it doesn't conflict with something you previously committed to. Then the question is, in a greedy algorithm design, which order should you go through the vertices? So one thing you could try is you say, well, we care about weight. So maybe we could go from the highest weight to the lowest weight vertex and pick greedily. So in this particular example, you'd first pick the 4, because that's the highest weight vertex. That would block the 3 3s, and then you'd pick up the 2 for an independent set of 6. What else might you want to do? Well, actually, if you think about it, it's natural to also incorporate degrees into a greedy heuristic. Why? Well, when you pick a vertex in your independent set, it blocks all of its neighbors from being chosen later. So another natural thing to do is somehow normalize by the degree of a vertex to strive for high weight, low degree vertices. And so, for example, if you ran a ratio heuristic like that in this instance, you'd get the maximum weight independent set of weight 8. Now, in any given set of instances, one of these two rules may be better than the other. And in fact, there's no reason to think that simple midpoints of these two algorithms wouldn't be better in still other application domains. So just the simplest thing you could do to interpolate between these two greedy algorithms would be just to look at weight divided by degree plus 1 raised to some power p, between 0 and 1. So p equals 0 corresponds to order by weight, p equals 1 corresponds to ordering by ratio. Okay? And so given a class of instances, you might want to know how to set p. Notice this is an infinite family of algorithms. For any choice of p, for any 2 choices of p, I can find you an instance where the algorithms will do different things on that instance. Okay? All right, so how should we think about application-specific algorithm selection? Well, I'm going to propose just a pack-style model. Okay, really totally bread and butter pack-style model. So there's going to be an unknown distribution, f over inputs. Okay, so when we talk about a domain or the special features of a domain, we're not going to be forced to articulate what those features are, what's the special structure. We're just going to assume that there's some unknown distribution from which instances you have to solve are being drawn. Okay? You never find out what this unknown distribution f is, but you do see some IID samples, Z1 through ZS, so S samples. Okay? Based only on these samples, and without other knowledge of the distribution, you must then decide what algorithm you want to run. Okay? So that's the goal. And so what algorithm do you want? Well, you want to do as well, approximately, as if you knew the distribution up front, capital F. Okay? So you're allowed to use any algorithm in C. You'd like to use the algorithm that gets the expected cost with respect to the unknown distribution as small as possible. So fastest average running time, smallest average solution quality, and so on. Okay. So one line of work which is sort of similar in spirit is self-improving algorithms. Though the difference there was, so they were thinking about sorting problems and problems in computational geometry. They were really focused on what one might call sort of the representation error part of the learning theory. Namely, they wanted sort of simple algorithms which are information theoretically near optimal, whereas the work here I'm really focusing on the sample complexity. Okay, so the sort of the generalization error, if you will. Okay. Anyway, so this is sort of the general setup for the first half of the talk. Any questions about that? Yeah.
How can you measure this if you don't know how?
How can you so it's only in the analysis, right? So we want to prove a theorem which says this is how well we're doing. Okay. Now you're sort of right that at the end of the day, how do we actually do this? We're going to compute this on the samples, which we have, and then we need to prove a theorem though that says the estimate we get from the samples is close to the actual statistic. Yep. Yeah, so it's all parameterized by the family of algorithms. For those of you that know some learning theory, there's going to be some, you're going to see the standard trade-offs, which is sort of, the bigger a set of algorithms you use, kind of the more things you're going to be able to do well, but the harder it will be to learn the right algorithm in any given situation. So there's this, as you add complexity to the set of algorithms, it gets harder to learn, but you do expect to do better if you do successfully learn. So the way you'd often think about this is you really probably more the way it works is, what you have are these samples, right? So you don't get to pick S, probably you have S. I mean, you could imagine going and harvesting more data, but suppose you just like had S. Then that would sort of, so then the theory will give you advice about, okay, here's the level of algorithm complexity you can handle given that you have S samples. Okay, so you sort of use the richest class of algorithms you could, given that you were confident you could generalize from your set of S samples. Yep.
Can you also allow, let's say, a low complexity combination of algorithms?
Yes, you can. I'm not going to say much about this, but one thing that's just a really nice consequence of basically the machinery that we use is if you, for example, take like the max of 2 greedy algorithms or like Q greedy algorithms, the sample complexity is just going to grow linearly in Q. And there's lots of other combination operations where, again, the machinery used, it just handles it very elegantly. Yeah, good question. Other questions?
The cost of computing the goal itself.
So of actually, so the cost of computing this function. Yeah, we're not, or.
The identification of a star, it may take a long time. You may give up halfway. If there are a lot of algorithms to consider, you may sit forever.
That's right.
Trying to identify which is the best.
You're absolutely right.
Let's not compute it.
Exactly right. So Hood's pointing out that at the moment I'm only talking about sample complexity. I'm just saying information theoretically, how many samples S are necessary and sufficient so that you can learn the best algorithm from C. You could also ask about the computational complexity. So ideally what you'd like to have is computational complexity polynomial on the number of samples. That's not generally what we get. So that's sort of an open question which, I and other people are working on too. So that's largely open. So this is going to be really just, what I'm going to do here is really like the first question you would ask, which is just like the sample complexity questions. Let's get those right, and then we can kind of move on to, other territory. But yeah, the focus here is just information theoretic. Thanks. Other questions? Okay. All right, so that's the kind of questions I want to answer. 4 various classes of algorithm C that we might care about. How many samples S are necessary and sufficient to achieve this goal? Okay, that's what I want the theorems to be about. All right, so how do we do this? So how do we bound the sample complexity? How do we argue that a certain number of samples are sufficient? Well, so this actually turns out, so what are we trying to do? We're trying to learn the best real-valued function. So this is totally in the wheelhouse of statistical learning theory. And there's a tool from that field that we're going to use called the pseudo-dimension. I'm not going to define it right now. I'll define it shortly. But if you know what VC dimension is, you trust me, you know what pseudo-dimension is too. The point here, so what I want to instead first make clear on is like, why should you care about this? So what consequences does it lead to, and what are some examples? So the first thing to know is that having low pseudo-dimensions, we're talking about a class of algorithms. Okay, so say like, those 7 SAT solvers or that family of weighted independent set algorithms parameterized by P. So we have the set C. That set is going to have some pseudo-dimension, and if the pseudo-dimension is small, that's a sufficient condition for having low sample complexity of learning the best algorithm from that set. Okay? So this is a sufficient condition for proving sample complexity upper bounds. Specifically, the sample complexity dependence is linear on the pseudo-dimension, and then quadratic in the error that you're willing to tolerate. Okay? So the algorithm, at least sort of naively, the algorithm would be just, find the best algorithm on the samples. Okay, so you have your S samples, try every algorithm. I know that doesn't make sense if it's an infinite set, but we'll get to that. So try every algorithm from C on each sample, see which one does the best on average in the sample, and then just sort of commit to that for future use. Okay? And again, so the guarantee is if you choose the algorithm from samples in the obvious way, then it will generalize, okay, if you have samples proportional to the pseudo-dimension. So that's the first point. Why is it interesting? Because it gives you upper bounds on sample complexity. Okay, but so are there any good examples? Right? So this is only going to be interesting if classes of algorithms that we care about actually have low pseudo-dimension. Okay? So not all classes of algorithms are going to have small pseudo-dimension, but lots of ones that you might be interested in do. Okay? So for example, the weighted independent set example, where you parameterize by p, so even though there's an infinite number of algorithms, in fact, the pseudo-dimension is only logarithmic in the number of vertices of the independent set instances that you're solving. Okay? Good. And then you get similar results for lots of other things. I'll say a little bit more about greedy algorithms, but the point of this slide is just that there's lots of different examples. Okay? And so again, keep in mind, sample complexity of learning the best algorithm is linear in whatever you see here, and quadratic in the error parameter. So for example, if you want to choose the best p from samples for weighted independent set, you're talking about a logarithmic number of samples. So the computational complexity, to get back to Ehud's point, the computational complexity is going to be exponential, at least for what we do, is exponential in these parameters. But actually, so if the dimension's logarithmic, you actually get a polynomial time algorithm for learning the right thing to do as well. Yep?
I mean, the pseudo-dimension, so can the algorithms need to be Lipschitz?
Yeah, they don't, and that's exactly sort of the technical challenge, and I won't have the opportunity to tell you about this. So the question was about sort of, how do you prove this? If it's an infinite class, so the first thing is easy. Okay, so if you have a finite set, then the pseudo-dimension is at most logarithmic in the size of that set. That'll be clear from the definition when I show it to you on the next slide. But then there's a question of like, okay, for an infinite set, how would you do this? So the first thing you'd think about is you say, oh, well, if there's a Lipschitz condition, i.e. like nearby algorithms, like nearby values of p, always act basically the same, then you can just pick a net, i.e. you just pick sort of a fine discrete grid in the parameter space, you try all of those, and you're done. But if you think about it, for weighted independent set, you do not have a Lipschitz condition at all. Right, so you tweak p just a tiny bit, that could change like the very first vertex that you choose in your independent set, which could then have arbitrary ramifications as you process the rest of the vertices. So sort of the technical challenge here is why, without Lipschitz and being infinite, how can you do this? And I guess just in one sentence, what you can say is that, well, in hindsight, so given a set of samples, if you look back and in your mind imagine running every possible algorithm on your samples, the number of different trajectories you could see does not scale very rapidly. Okay, so for a fixed finite set, then you have a reasonable dependence on the number of different behaviors that you'll see. So that's what drives these bounds. Okay. All right, so pseudo-dimension. So let me just say, like, you really don't need to understand this definition for this talk if you don't feel up for it. But I feel like I owe you a definition. It is kind of showing up in all the theorems. I guess the takeaway, for those of you that know pseudo-dimension, the takeaway is it's the same as VC dimension. For those of you that don't know VC dimension, the takeaway is just that, while the definition may be kind of long, as I showed you on those examples, you can prove bounds on it actually pretty easily. Okay, so it's quite easily analyzable despite the length of the definition. So VC dimension, how does it work? So why can't we just apply that off the shelf to what we're talking about now? There's just a type check error. Right, so VC dimension is about binary functions, binary labeling functions. Okay, so given a sample, it's either true or false. It's yes or no. We have real valued functions, right? We have algorithms. We're looking at the performance profile. Okay, but so like, what's an easy way to change a real valued function into a binary function? You just threshold it. Right, so you pick a threshold and you ask, is the real valued function above or below the threshold? And that's it. So you just throw in thresholds into the VC dimension definition. You get pseudo dimension. So slightly more formally, VC dimension says how big a set can you shatter. So this, in our context, this would be sort of a set of inputs. Shattering means, as you range over every hypothesis in your class, you see every possible binary labeling of zeros and ones of the sample. So here it just says there exists some set of instances, there exists a set of thresholds, so that as you range over algorithms, you see every possible combination of being above or below the thresholds. And then the biggest set you can shatter is the pseudo dimension. Okay? All right, but again, if that was too fast, you really don't need it for the rest of the talk, so don't worry about it. Okay, I think I'm going to skip this in the interest of time, okay? All right, so in this first part of the talk, there's just one final thing I want to say, largely because I think it suggests a really nice open research direction where I feel like there's tons to do. And this starts getting at sort of, some data science issues. And so this is about choosing the right parameter for your algorithm, for parameterized algorithm, especially for machine learning algorithms, which typically have lots of parameters. So we only took like the most baby step manageable. Okay, so we thought about gradient descent, which of course is the workhorse for most large-scale machine learning these days. And we just looked at the parameter of the step size. Okay, so in a given iteration of gradient descent, how far do you go in the opposite direction of the gradient? Okay, so that's sort of a key parameter in gradient descent. So if you sort of go to a book on convex optimization, what does it tell you about choosing the step size? Well, what you'll usually see is it'll say, well, suppose the function you're trying to minimize is strongly convex. Okay, so you have some lower bound on the eigenvalues of the Hessian. And then it will say, well, then if you choose your step size to be this or smaller, you are guaranteed to have convergence to a nearly global minimum. Okay? That's what you'll see in any convex optimization text. Now, in practice, people use much larger step sizes. They're much more aggressive. Okay? So they're hoping to converge in much fewer iterations, make way more progress per iteration by taking a big leap. But they are running the risk that they actually never find the sort of right basin at all. Okay? And so you can imagine there's going to be some sweet spot where even though the theorems don't hold, you still get good performance. Then, of course, if you jack it up too far, you're just going to bounce randomly across the space. So a natural question would be, given some distribution over functions you want to minimize, how should you choose the step size? Again, that has really nice pseudo-dimension. And here, actually, we are using more like this net idea. We're using Lipschitz we basically prove Lipschitz properties of gradient descent. As you vary the step size, you can sort of track trajectories. They don't converge too much. And so therefore, you can use a net argument to do this. So again, I hope you take this just as a proof of concept that, first of all, this, so-called hyperparameter optimization, so choosing parameters of a machine learning algorithm, it translates very naturally into the existing learning theory machinery that's been built up over 30 years, and you can prove positive results, at least in sort of simple cases. But I think there's a lot more to do here. All right, so any questions before I segue, sort of switch gears and go to the second half? So let me now sort of make the connections between this work and algorithmic game theory and data science a little bit more explicit. So what I want to talk about now is not learning algorithms, but learning a good auction for maximizing revenue. So I'm not going to really assume that you know anything about auctions. And if you've never thought about auctions, I'm totally happy if for the rest of the talk you just think about an eBay auction as like the canonical example. So an eBay auction, so that's a single item auction. So you have one seller. They're selling exactly one thing. There's a bunch of bidders that might want to buy it. And a key word is evaluation. Okay, so evaluation is just the maximum willingness to pay of a bidder for an item. Okay? And so the assumption is that as the seller, you don't know what people are willing to pay. You don't know these valuations. That's why you're running the auction in the first place. So then the question, which comes up is if you're selling stuff, which auction should you use? Okay? This is actually a tricky question to do math about. So even just in an eBay auction, you don't have a lot of knobs to play with if you're selling stuff on eBay, but you do have one, which is the opening bid, or equivalently, the reserve price. So you might want to say, okay, I'm selling a Twinkie, as in this example, what would be the optimal reserve price? And the reason it's sort of hard to think about this is, for any reserve price you might pick, you might regret it later. Okay? Whether or not it's a reserve price that's good, it can only be sort of judged in hindsight after you see what people are willing to pay, which of course you don't know when you're picking the reserve price. If some sucker buys your Twinkie for $8,000, you're feeling pretty good about your choice of a reserve price of $8,000, right? But if it goes unsold for a long period of time, maybe you think you should have done something smaller, okay? All right, so how do we reason about this question? So probably you're thinking, well, surely economists have thought about this for a long time, right? They're in the sort of auction business, and they have. And the dominant paradigm in auction theory world is what we would call average case analysis, or Bayesian analysis. So what does that mean? So that means we're still going to assume you don't know bidders' valuations, you don't know what they're willing to pay. But here we do assume that you know a distribution, so the seller knows a distribution from which the valuations are drawn, F1 through Fn. I'll always be talking about independently drawn valuations, okay? So you still don't know the VIs, but you do know the FIs. Now we have a well-defined mathematical optimization problem. Okay? So given these distributions F1 through Fn, among all auctions in the world, find me the one that maximizes the expected revenue. Okay? So this is the optimal auction problem in economics. All right, so what do I mean by all auctions in the world? Well, for this talk, I just want you to think about sort of sealed bid auctions. So say in a single item auction, you'd collect one bid from each one bid from each bidder. You'd decide on a winner, or maybe nobody, and you'd decide on the selling price. eBay would translate to what's called the second price auction with a reserve. So that just means the winner is the highest bidder who clears the reserve R, if there is such a bidder. And then if there's a winner, they pay the higher of the reserve or the second highest bid. So in this particular auction, it's called a truthful auction because it's a dominant strategy to just bid your true valuation. And I'm going to be thinking only about truthful auctions in that sense for the rest of the talk. Okay? Again, key takeaway here is, given the distributions, there's a well-defined optimization problem of finding the optimal auction for these distributions. And the next thing you need to know is that this problem is totally solved. Okay? It's been totally solved 35 years ago. So Meyerson literally just said, you tell me your distributions, I'll tell you the optimal auction. Okay? And he just solved it in all cases, the one that maximizes the expected revenue. The auction even fits on one slide. The only tricky step is the first one. So in the first step, you collect bids from everybody, and you transform the bids into what are called virtual bids. So BI gets mapped to some phi of BI. You don't need to understand this formula for this talk. I just want you to notice one thing, which is that when you compute the virtual bid for a bidder, it references the distribution and density functions. Okay? So this is where the distributional knowledge is being taken advantage of in the description of the auction, in which auction you decide to run. Given these transformations, it then proceeds as you'd expect. The winner is just the person with the highest virtual bid, assuming it's positive. And then what's the price? The price is the analog of the second highest price, namely the lowest bid at which the bidder would continue to win. And that's going to be a truthful auction. Okay? So that's really cool. So we really know what is the optimal auction, single item auction in all possible cases. If bidders are symmetric, IID, all the distributions are the same, then actually this simplifies. It becomes a second price auction with a suitable reserve. So in other words, when bidders are IID, eBay, as long as you choose the opening bid properly, is actually an optimal auction, which is kind of crazy given how rich the design space of auctions is. Okay, you get something so simple that winds up being optimal. Now, when bidders aren't symmetric, when they have different distributions, then there's really no general simplification of Meyerson's mechanism. This is really what you have to do if you want to be 100% times optimal. You have to do this full-blown virtual bid transformation. Okay, so guess there's nothing left to do, right? So in light of Meyerson's theorem, pretty much nothing to say about revenue maximizing auction design. Well, not really, or at least not, some grumpy computer scientists came along and made a couple complaints about optimal auction theory. We all think it's amazing and beautiful and has lots of applications, but to extend its reach, there's a couple changes you might want to make. So the first complaint, which was also recognized in economics, says, well, if you look at the sort of the form of the auction you get, the optimal auction, it depends, in a really detailed way on your distributional assumptions. And one consequence of that is it's a relatively complex auction format. Right? So you have to do these sort of virtual bid transformation. It's kind of hard to understand what those things mean. And indeed, really, while there's special cases of these optimal auctions in the real world, as far as a full-blown virtual welfare maximizer, I'm unaware of any examples that have ever been deployed. So that's a little bit of an issue. So outside the IID case, it doesn't seem to match up with the auctions that people really run. The second question would be like, well, so this is a complaint even if you agree that you know the distributions. The second complaint, would be like, where'd you get these distributions anyways? Right? So why do I believe your distributions? And, so if you wanted to have a middle ground, you might say, well, in this day and age, I can at least imagine how you'd get a guess at a distribution, which is you look at bidding data from past transactions for comparable items, and you see what people did. And from that, you reverse engineer some, hypothesized valuation distribution, which you can then use to apply Meyerson's optimal auction theory. And so again, the question here, and this has been done in practice. So Ostrovsky and Schwartz, for example, they sort of optimized Yahoo's sponsored search reserve prices, and this is exactly what they did. They looked at bidding data, they reverse engineered valuation distributions, they said, what would Meyerson do? And then they did some approximation of what Meyerson would tell you to do. And so again, the question is, can we have theory which really very closely mirrors this entire thought process, okay, how this works? So using data to guide which auction that you pick. Okay, so each of these two criticisms, so this one just about the auctions being too complex, this one about assuming too much information, these have both sprung off really interesting threads of work in the algorithmic game theory community. I'll tell you a little bit about each separately, but then the main point of this last part of the talk is that actually what's going on in the two strands of work is very, very tightly coupled. Okay? All right, so let's begin with this, the complaint about these auctions being too complicated. So, for example, one representative result, so this is work with Jason Hartline from 2009, was to say that, well, let's give up on full optimality? Can we gain a lot of simplicity by just allowing sort of some reasonable approximation? Okay? And so we extended previous work about single item auctions, also Jason, with Chawla and Bobby Kleinberg. And we showed that in many single parameter settings, you don't even know what that means. That's just like the settings where Meyerson's theory works. So in the settings where Meyerson's theory works, and we know these virtual bid maximizers are optimal, if you do something simpler, namely, you just set one reserve price for each bidder, and then do something simple on top, welfare maximization. That's the analog of picking the highest bidder. So if you just pick one reserve price per bidder and then do welfare maximization, that gets you a constant factor approximation. It's not going to be optimal. It's not going to be as good as this theoretically optimal auction, but you do get a performance guarantee on this simple auction, which does start resembling things you actually see. Now, we called this paper simple versus optimal mechanisms, but we offered no definition of what we meant by a simple mechanism. We left it as kind of subjective. At the time, if you'd cornered me and said, no, really, what do you mean? What I probably would have said was, intuitively, think about the number of degrees of freedom that you have in one of these simple auctions versus in the full-blown virtual bid maximizers. Here, with these reserve prices, it's clear you have exactly 1 degree of freedom per bidder. Okay, you have 1 reserve price per bidder. Other than that, everything is determined. Whereas with Meyerson's mechanisms, with these virtual transformations, you intuitively have an infinite number of degrees of freedom, right? Because you have this arbitrary function from bids to virtual bids. So that's sort of the wishy-washy answer I would have given at the time. There's a lot of great work going on approximation guarantees for simple mechanisms. So here's sort of one of the greatest results from the last couple years in this thread by Bob F. et al. From Fox 14. So they said, well, let's think about just one buyer, but multiple items. Okay? And it turns out, even with one buyer, when you have multiple items, it's actually much more complicated than the earlier settings that we were talking about. For example, we have no analog of Meyerson's optimal auction theory in this case. We actually have no idea what the optimal auction looks like in general. Even just one buyer, k items, multiple items, additive valuations. So we don't know what the optimum is, but Bob F. et al. Do propose a simple mechanism which is provably close to the optimal revenue. Okay? So they have an upper bound on the optimal revenue, and their mechanism gets within a constant factor of it. So what is their simple mechanism? Well, they say, here's one thing you could do. Again, remember, one buyer, k items. So one thing you could do is you could say, well, let me put all the k items into a single bundle, and I'll give the buyer a take it or leave it offer for all k items. Okay? And that's all the buyer can do. Either it takes everything or it takes nothing. That's one option. The second option would be to price items separately. Okay? So for each item, you put your own price. The buyer can then pick whichever subset of the items it wants. And of course, it's going to look at its value minus its price. Now, in general, neither of those is optimal, but Bob F. et al. Proved that the better of these two mechanisms is, in fact, a constant factor approximation. Okay? So that's a very cool result. And then there's Andy Yao in SOTA 15 extended this also to multiple buyers with a somewhat worse constant factor. Okay? So this is getting quite close to the state of the art in simple versus optimal mechanisms at this time. All right. So that was just sort of some background about what's been going on. How do we do theory relevant to this critique of the complexity of Meyerson's optimal auctions? Yeah.
When you say approximation, you mean is what becomes large or small?
So neither. So there's no limit. You could imagine also having limiting versions. Good, yeah. So basically it means that there's some uniform constant so that no matter how many bidders you take, no matter how many, so say in Yao's result, no matter how many bidders there are, no matter how many items there are, no matter what the valuation distributions are, the expected revenue of this mechanism will be within this universal constant factor of the optimal expected revenue. Thanks. Other questions? Yep. Not so bad, actually. So once you've decided to sell the grand bundle, then basically what you should just do is sort of the monopoly price for the grand bundle. So in other words, an obvious sort of greedy heuristic. If you've committed to selling the item separately, you may as well just use a monopoly price for each of those items. So it really is, yeah. So it's a nice result. So it's a mechanism you could really imagine using. Yeah. Other questions? Okay. So remember, there was also this second critique, which was saying, well, so all of this work has been, the thinking is the distributions, but then you kind of use the distributions kind of in a modest way so you get a simple mechanism. But what if you actually aren't privy to these distributions at all? And so now, no surprise, I mean, a pack learning type setup is a very accurate model for how people tend to think about this problem. So again, there's an unknown distribution. Okay, so now it's over valuation profiles. As a seller, you get some samples. That's all you know about the distribution is S samples. Again, the natural interpretation here would be bidding data from past auctions for comparable transactions. And then based on the sample, you need to choose what auction to run, excuse me. Okay? So maybe there's a restricted family of auctions, or maybe you're just optimizing over everything. Okay? You could try that too. And again, the goal is to do almost as well as if you knew the distribution up front. So for example, in single parameter settings, the goal is to do almost as well as Meyerson's optimal auction. Okay? All right. So this idea of learning good auctions from samples has really kind of gone viral in the last couple of years. So there's an early paper by Edith Elkin in SOTA 07 that was way ahead of its time, but was really sort of talking about these issues of learning a near optimal auction from samples. It's a little bit implicit, but mostly in there. And then really around 2014, a lot of people sort of independently proposed, this sort of general idea of sort of pack learning for a near optimal auction. Okay, so as you'll see for the rest of the day, there's tons of other related work, kind of slightly further away. This is just the related work which is on exactly this, exactly kind of a pack model and learning a near optimal auction from samples. Okay, and so there's a lot going on in the area. Okay, and again, just like we had for algorithms, so we're going to use it's the same pseudo-dimension concept. So before we thought of an algorithm as a real valued function, now an auction is a real valued function, from valuation profiles to the revenue it attains. We're trying to find whatever the auction is that gets that expected revenue as high as possible. So again, it boils down, or a sufficient condition is to bound the pseudo-dimension of the auction class. And again, for this to be interesting, you need good examples. So here's some examples. Okay? And the main takeaway here is just that, the pseudo-dimension you get actually does correspond quite closely to this idea of the number of degrees of freedom that you have in the auction. So for example, if you have bidder-specific reserve prices, so one reserve price per bidder, you can prove that the pseudo-dimension is O of n log n. It might well be linear. We don't know. It's certainly at least n, but we can prove a bound of n log n. Similarly, in the Bobiev et al. Setting with one buyer and k items, if you just look at mechanisms that either do a grand bundle or sell items separately, notice this is the max of two mechanisms. So this gets back to the earlier question about composing these different mechanisms. So here you can prove a bound of k log k. Again, the right answer might well be k. On the other hand, indeed, these virtual welfare maximizers necessary for full optimality, you can prove a lower bound that actually there's no bound on the pseudo-dimension of that class of auctions. Okay? So there seems to be really good, it seems to correspond well to our intuition about the number of degrees of freedom as a quantification of the simplicity of these mechanism design classes. Okay, so let me just tell you a little bit of sort of what we prove. So as I said, there were these two critiques of optimal auction theory. The first saying things are too complex. That motivated people to have simple near optimal auctions. The second, that the informational assumptions are too strong. That motivated learning from samples. So what these theorems are saying is that basically all of the work which was done in the first part, all of this work on simple near optimal auctions, because they're simple, they're also easy to learn. Okay? So we want to have a general sort of positive learning statement for any of the simple auctions, including the two examples that you've seen. Okay? So that's the idea here. We want to say that any simple mechanism can be learned from few samples. Okay, so good. So let me start with a one-buyer setup. So this is like exactly in the Bobiev et al. Setting. And so let me define a class of auctions. And this is going to be our definition of what we allow as a simple auction. So what you're allowed to do is choose a partition of the items, okay, and set a price on each group in the partition. For example, grand bundling, that's a partition of size 1, and you set a price on it. Item pricing, that's a partition into the singletons. Okay? So take whatever partition you want, and you can have many such partitions, say P partitions. Okay? So any single buyer auction of that type, you can prove that the pseudo-dimension of that class is linear in K and linear in P. Okay? So K is the number of items, P is the number of partitions. Okay? I'm omitting some log factors here. Okay? But the log factor is K times P. All right? So that's the first thing. Anything which is sort of based on partition by prices, you get a good pseudo-dimension bound. This covers kind of all of the single buyer mechanisms for which people have proved simple versus optimal results. Let me see. Okay. So a little bit about how this works. So just to peer under the hood. Some of the techniques here, which we draw on from learning theory, I think are really nice. So we need to bound the pseudo-dimension. So we need to sort of bound the biggest size of a set that can be shattered, which sort of boils down to saying, for a fixed set of valuation profiles, how many different things could happen as we range over all of the mechanisms in our class, all of the auctions in our class. And so the way we do that at a super high level is we fix a collection of valuation profiles, a collection of samples. And we first partition the auction space, so we bucket auctions, according to their allocation. Remember, an auction has two parts: the allocation, who gets what, and the payments, who pays what. Okay, so we factor it into two parts. We first bucket auctions according to the ones that make exactly the same allocation decisions across all the valuation profiles in this sample. Okay? So two auctions are equivalent in this sense if they always give the same items to the same people. That doesn't mean they charge the same prices. So then, for each of these buckets, we need to also analyze things and say not, what happens within a bucket is well structured. That tends to follow because, with the allocation fixed, the revenue is going to be a linear function of things like reserve prices and valuations and so on. Okay? Now, to implement the first step, so the way I just told you this naively is not going to work. Okay? So I said bucket auctions according to what allocation they make. But even just think about a single buyer with k items, right? There's 2 to the k different applications, 2 to the k different allocations you might see, every possible subset of items, as you range over the auction space. So if you do this naively, you're going to get a 2 to the k on the sample complexity bound. So how do we get it down to k? So here we use this idea of linear separability by Daniel A. and Shalif-Schwartz. So they say, well, suppose not only do you have these buckets, but each bucket is defined as the maximizer of a bunch of inner products. So the idea is you put up a bunch of vectors, and as long as you can always define the maximum as as long as the allocation always arises as the maximum of a bunch of inner products, then the pseudo-dimension is proportional only to the number of inner products that you use. Okay? So this is the trick we use to get down from 2 to the k to k. And then Daniele and Shalif-Schwartz, they prove this really cool result, which says whenever you have linear separability in this sense, you have what's called the compression scheme. So a compression scheme says whenever you have, say, an arbitrarily large number of samples m, there's always a subset of, say, D samples, which summarizes how you want to do the classification. Okay, so if I just tell you these D samples, from that you can reverse engineer what the labels are for all M samples. And then it's been known for a long time that hypothesis classes with good compression schemes actually have low sample complexity. Okay, so that's just a little bit of the details for those of you that know some learning theory. Okay, so I showed you a theorem for the single buyer case. So there's also an extension to the multi-buyer case, and this is basically the limits of what we know how to handle. And so what we do here, and this is sort of inspired by a composition theorem of Sirkanis and Tardos, is we prove what I might call a sequential composition theorem in this setting for sample complexity. So we take the single buyer auctions that we had previously, so these partitions, you set the prices, you pick the best one. Now we imagine that we go through these multiple buyers one at a time, and each time we reach a buyer, we apply one of these single buyer mechanisms. Okay? And so there's a general theorem you can prove that the pseudo-dimension, if it's small for each of the single agent mechanisms, it's also small for this multi-agent mechanism. If it's anonymous, in the sense that the prices chosen in the single agent mechanism do not depend on the agent, you actually don't blow up at all. If you can have different prices, non-anonymous prices, so different prices for each of the n agents, then it's clear that the number of degrees of freedom are blowing up, and indeed we suffer an extra n log n. But the reason this works is because linear separability, which I mentioned on the last slide, this composes really nicely. Okay? And the final thing I want to say for sort of the auction experts, so as you know, a lot of the simple auctions that have been analyzed are sequential auctions, so this covers those immediately. But actually, there's some auctions we normally think of as single shot, which have equivalent sequential implementations. And so Yao's multi-buyer auction is one example of that. So we can handle the case of Yao's family of mechanisms. All right, so I'm all done. Let me just wrap up. So I showed you how this bread and butter pack formalism is really good for sort of accurately modeling how people approach two different things. The first thing is this idea of just, given a computational problem, which algorithm should you use? How do you figure it out from synthetic data and so on? And then the second thing was about learning near optimal auctions. So again, the traditional theory there is Bayesian, assumes you know a distribution. I think this pack approach sort of makes it more operational. Okay? So it really says if you have enough data, then you can do just as well as if you really could implement the true distributions from Meyerson's auction. And then the sort of the culminating results in the second part was this idea that people so far have been kind of using simplicity in an undefined way, but if you actually sit down and define it, all of the simple auctions people have studied are automatically learnable. So whenever you can have a near optimal auction from known distributions, you can also have a near optimal auction from unknown distributions given samples. And I do just want to conclude with a couple plugs of open questions I mentioned. Computational complexity, almost entirely open. This has been all about sample complexity. And then let me stop there. Thanks.
questions?
Yep.
So regarding pseudo dimension, an upper bound on pseudo dimension says that you can learn from samples.
Right.
But what does it? I mean, what does the lower bound indicate? Because I mean, isn't it just a way? I mean, doesn't it just say that this approach fails?
Yeah, so the question is about a converse, yeah?
Yeah.
Right, so in general for pseudo-dimension, there isn't a converse. You can have low sample complexity even though you have high pseudo-dimension, although that's not the case in any of these examples. But then there's a notion of fat shattering dimension. And so it's you know, and so it's sort of easier to upper bound. Sometimes you have smaller bounds on fat shattering dimension, and that actually characterizes sample complexity. So you actually, well, not quite, so it characterizes uniform convergence. So if you really want to have an accurate estimate of everybody's expectation, fat shattering dimension tells you the number of samples that you need. Sort of for the examples here, all of these concepts kind of collapse, and it's not really worth making the distinction. Yeah.
So I don't know, maybe I missed something in the beginning, but you made any assumption on these distributions, like
So
samples from some really weird distributions presumably don't mean much, and
I mean, the one assumption is this. So you have some knowledge of the range of your performance metric. So like you know the running time is going to be between, you know, A and B. Maybe because you time out, you know, B is actually, you know, you have control over B. Or, you know, for auctions, there's some limit on how much money you could possibly get from this auction in this domain. And so there's two ways to do it. You can either, if you really want to have additive approximation error epsilon, even as h grows large, then the sample complexity better depend on h, and it does, it's h squared. A different regime would be, it's like, oh, well, you know, if I'm expecting for the running time to be ballpark h, if I'm expecting the revenue to be ballpark h, maybe I can allow approximation epsilon h, and then h doesn't show up in the sample complexity bound, it's just d over epsilon squared. So that's the main thing which sort of disallows truly pathological distributions.
For those of us who are not in computer science, so when you say approximation is good if there is some k
Yeah.
that uniformly bounds
Yeah.
the error, I
Yeah.
guess. How small is k?
So it varies with which result I talked about. Obviously, you want it to be as close to 1 as possible. 1 is good. So, I mean, here's the way I think about this. I mean, you know, if you're taking any kind of like worst case over any reasonable set of distributions, there's going to be some sort of small example where you're not optimal. And nothing's going to infinity in this small example. So you're never going to be, you know, arbitrarily close to 1 without taking some limit. So you're stuck with constants which are bounded away from 1. Now, you know, for those of us who do approximation, you kind of get used to the fact, it's sort of just like a sad fact of life that worst case approximation, you rarely see things better than 1/2, maybe 3/4, that kind of thing. But, you know, the takeaway from the theory is often these bounds you can parameterize. So you can sort of nicely say, okay, so suppose I assume more and more on the distributions, then I can prove tighter and tighter bounds. I haven't stated any of those in this talk, but often in these papers, the authors will go ahead and say, oh, well, give me more control over the tails of this distribution, and I'll give you a still better bound. And you know, I would encourage all of us to continue to pursue parameterized bounds in that form.
So I have a question about mechanism design. So there were some of these papers you talked about which had already shown that these simple mechanisms were good, and you were saying also if you wanted to learn those mechanisms, those are good. If I wanted to design mechanisms for low pseudo-dimension,
Yeah.
Are there principles or frameworks for that?
Yeah, it's a good question. Yeah, so part of the work with Jamie Morgenstern, we offer a sort of example of that. So I omitted it from the talk for time, but so just think about like a single item auction. So I mentioned the result of Jason's with Shuchi Chawla and Bobby Kleinberg, where they say you can get within a factor 2 if you use 1 reserve price per bidder. And then you might want to think about, you know, well, what if I use a sort of slightly more complex mechanism? Could I have a sort of smooth trade-off between how complex the mechanism it is and how close we get to Meyerson's optimal auction? And so a natural way to do that is instead of just having 1 reserve price, which is like a single threshold for each bidder, you could have T thresholds for each bidder. So then you just sort of bucket bidders you sort of sort bidders according to how many thresholds that they bid above, and then that's how you choose the winner. And indeed, there you get this smooth trade-off between how close you are to optimal and the pseudo-dimension. The pseudo-dimension scales linearly in the number of reserve prices that you use. And I think, I'm trying to remember to get a 1 minus epsilon. You know, I think T just has to be like 1 over, I think it has to be 1 over epsilon to get within a 1 minus epsilon approximation. But again, I do want to point out, I mean, this is just like one initial proof of concept. You could imagine actually a very, you know, it's easy to imagine a rich research literature which formally studies, you know, these kinds of representation error versus generalization error trade-offs, and really asking, for example, so given a budget on pseudodimension or more generally sample complexity, what is the best possible approximation ratio you can be guaranteed, okay, within some auction class with some budgeted pseudodimension? And not many people have asked questions like that, but I think they're actually quite relevant questions, so I hope to see work on that.
All right, thanks a lot, Tim.
Thank you.